In this chapter we're going to look at sound beams and how they behave in space as they propagate through the media. A couple assumptions we're going to make for this chapter is that sound is made from a single element piezoelectric crystal. The crystal that is going to make the sound is a disc-shaped crystal, and it would expand and contract. It will expand and contract along the width of the crystal, or the thickness of the crystal, as the electrical voltage is applied to it. The sound is going to start out as the size of the crystal, and this should make sense. It can't start out larger than the crystal, and it's not going to start out smaller than the crystal. It'll just start out the size of the crystal, and then it will propagate along the axis of propagation as a longitudinal mechanical wave would. There is an area known as the focus where the sound reaches its narrowest point. And so the focal point is the narrowest, and the width of the sound beam is half of that of the initial width at the transducer. So the sound will just naturally focus down to half its size. And this is due to something called Fresnel effects or near zone effects, and these are this focusing occurs because the wave is interacting with itself causing constructive and destructive interference patterns within itself and narrowing it down. This is called a Fresnel effect. Where this Fresnel effect is occurring is called the near zone, and that is the distance between the crystal and the focus. You can see it also has this name, focal length. It is the depth that the sound travels until it is focused. So the near zone length and the focal length are synonymous. They are the same thing. And it's kind of remarkable that the near zone length, the sound will start out as the diameter of the crystal. It will narrow down to half the diameter, and then at a distance equal to the focal length beyond the focus, the sound will again have the same diameter as it had at the crystal. So it's a very symmetrical narrowing and spreading of the sound beam. This area where it's spreading past the focal zone is known as the far zone, okay, or the divergence zone. Okay. So we call this near zone area the near zone. It is the focal length. It also has the name the Fresnel zone because of the near field effects occurring. And then this far zone, which is the divergence as the beam spreads apart, is called the far field or the Fraunhofer zone. And this divergence will continue past two focal lengths into infinity as the beam continues to spread and spread farther and farther, and eventually is just absorbed as heat by the surrounding tissues. So this far zone we call the far zone, or it's also named after Fraunhofer, who studied divergence. So it's the far zone or the Fraunhofer zone. Okay, the near zone is the near or Fresnel zone. The far zone is the far or Fraunhofer zone. The near zone is also the focal length, and the far zone, being the far field or Fraunhofer zone, is also known as the divergence zone. So at the focus, the beam is 1/2 the crystal diameter. At two near zone lengths, the beam diameter is again equal to the crystal diameter. And then beyond two near zone lengths, the beam continues to diverge until it is spread out as wide as you possibly could want it to be. Around the focus, there is an area we call the focal zone. The focal zone is defined as the area where the maximum intensity, which occurs at the focal point, well, let's just restate that. At the focal point is where the area is the narrowest, and we will find the maximum intensity of the sound beam. The focal zone begins at 1/2 of that maximum intensity and ends at 1/2 of that maximum intensity. So the focal zone is considered the region around the focus where you have 1/2 the maximum intensity at the beginning and end of it. This is a very good area for imaging because the beam is the narrowest. So let's summarize what we've talked about. The beam diameter at the transducer is going to equal to the transducer diameter. The beam diameter at the focus is going to equal 1/2 the transducer diameter. The beam diameter at two near zone lengths away from the transducer is going to equal the transducer diameter. And at distances deeper than two near zone lengths, the beam diameter continues to diverge and becomes larger and larger than the crystal diameter. So, summarizing all of this, the sound beam is emitted from the crystal. It progressively narrows until it gets to the focus. This is known as the Fresnel zone or the near zone. The focus is 1/2 the crystal diameter. The focus marks the end of the near zone, and the distance from the transducer to the focus is known as the near zone length, or NZL, near zone length. The far zone is where divergence occurs, and the focus also marks the beginning of divergence. At two near zone lengths from the transducer, the beam is again the size of the crystal, and as we go beyond that, the beam continues to diverge and becomes larger and larger. So we can summarize that the beam diameter at the transducer is the size of the transducer. That should make sense to you. At the focus, it is 1/2 the transducer diameter due to near field effects. At twice the focal length, the beam is again the size of the crystal diameter. Deeper than two near zone lengths, the beam continues to widen and becomes wider and wider. We may ask ourselves, what determines the actual focal depth? We know it occurs from Fresnel effects, but what actually determines that? Well, there are several things. So the focal depth is determined by two things: the transducer diameter and the frequency of the sound. Okay, these are what the primary determinations are. This is for a fixed focus system such as what we are using describing today. Systems that have adjustable focus are called phased array transducers or phased array systems. Okay. These we can adjust the focus up to a point. The early systems that were used a fixed focus, which had the focus solely determined by the transducer diameter and the frequency of the sound. So, determining the focal zone. The focal depth, or near zone length, is proportional to the diameter of the crystal squared. Okay. The focal depth and frequency are related. The near zone length is proportional to the frequency. So, let's restate this. As the diameter goes up, the focal zone length goes up greatly to the power of 2. As the frequency increases, the focal zone length or the near zone length increases in a linear relationship, linear relationship. So we have an equation that we can utilize, and that is this one. The focal depth is related to the diameter squared times the frequency in megahertz divided by 6. Okay, if you use this equation, you get a focal depth in millimeters. Okay, so your diameter has to start in millimeters, your frequency has to be in megahertz, and you will be able to determine exactly what the focal depth is in millimeters. A more precise equation which exists is that the focal depth is equal to the diameter in millimeters squared divided by 4 times the wavelength in millimeters. And that will give you the exact depth. So the top one's an estimation, the bottom one's exact. They both work. Okay, they both are essentially equal. This one on top is easier to remember because the frequency is on the same side of the divisor as the diameter. So you know that as the diameter goes up, the near zone length increases greatly. As the frequency goes up, the near zone length increases. Okay. This one's a little harder because the frequency is hidden within the wavelength. As you recall, the wavelength is equal to the speed of sound given by the symbol c over the frequency f. And so the frequency gets hidden within this equation, but it's right out here in the first one. So, again, both of these equations work, and they can help you determine the near zone length or the focal depth. As sonographers, we always have this dilemma where if we want better imaging, we use higher frequency, and this does give us a deeper focus. But if you remember from the interaction of sound and media, as sound travels through tissues, it attenuates, and the higher frequency you get greater attenuation. So by just raising the frequency, this is a terrible way to get a deeper focus because the attenuation becomes so great that we cannot penetrate the tissue and image deeply by just increasing the frequency. But we can increase the diameter of the focus in order to get our focus. We can increase the diameter of the crystal in order to get our focus to move deeper. And so that is what we do. In order to make the focus deeper, we make the transducer crystal a greater diameter. Unfortunately, this makes the beam width somewhat thicker, which will decrease our lateral resolution. We've already talked about what axial resolution is. So lateral resolution is the beam width. We would like that as narrow as possible, but we're limited by physics in order to get it there. So in the far field, we have the beam diverging. So this is the divergence beyond the focus. And the sound beam diverges or spreads out related to the diameter of the crystal when it begins. So a larger crystal diameter will have a much smaller angle of divergence in the far field. A small crystal diameter will have a much greater angle of divergence. And so when it gets to the far field, it will spread out much, much faster. What does this divergence angle depend on? Both the transducer diameter and the frequency of sound. So crystal diameter and beam divergence are inversely related. The smaller the crystal, the greater the angle of divergence. The larger the crystal, the smaller the angle of divergence. A way to restate that is a larger crystal improves resolution in the far field. We get less spreading of the beam in the far field. Frequency and beam divergence are also inversely related. Lower frequency gives a shorter or a greater angle of divergence, and higher frequency gives a smaller angle of divergence. Okay? So again, higher frequency improves resolution in the far field. However, it also increases attenuation. So with beam divergence, there are some equations we can utilize to actually measure beam divergence. The sine of the divergence angle is equal to 1.85 divided by the diameter times the frequency. Okay. Another way to rewrite that by swapping out wavelength for frequency is that the sine of the divergence angle is 1/2 times the wavelength divided by the diameter. And everyone's now saying, oh, but I'm not going to be able to do sines on the test without a calculator. Correct. What you need to remember is that the divergence angle is inversely proportional to the diameter and the frequency, and directly proportional to the wavelength. If the diameter goes up, the divergence angle goes up or goes down. If the frequency goes up, the divergence angle goes down. If the wavelength goes up, the divergence angle goes up. Earlier we talked about different types of scattering, and we mentioned something called Rayleigh scattering, where the sound reflects off of a very small scatterer and reflects in all directions, or as a circle more or less. If our transducer element is small enough, it will affect the sound the same way. The sound will start out as a little spherical wavelet and just immediately diverge in a V shape. These are known as wavelets that are occurring, and they can interact with each other, forming wave fronts. Okay. So these are known as wavelets, or Huygens wavelets, or spherical waves, or simply diffraction patterns. Okay. The important point to remember of this is that these wavelets can add together and form a wavefront. Okay. So Huygens' principle states wavelets added together form a wavefront. So I'm going to go off on a bit of a tangent here. If you get out a telescope and you look at the planet Saturn, you will see a planet surrounded by rings. Well, these are not actual rings. They are small little particles of ice that float around the planet. However, when we look at them, it looks like a flat disk. And that is because the little pieces of ice reflect light from the sun, and they add together and look like solid disks. This is actually what Huygens studied when he came up with his principle that the wavelets will form a wavefront. So what we see is the disks of Saturn are actually little tiny ice particles floating around the planet. But the sound or the light comes to us as a wavefront of light, and it looks like a solid ring. Just like the sound emitted from a transducer with many, many tiny transducer elements will come and form wavefronts and act as a solid wave because of Huygens' principle. So here we can see an actual wave coming off of a transducer, and as it travels down the image, you can see it narrowing and then starting to diverge slightly at the very bottom of the picture. So sound wave near field effects, and we talked a little bit about this before, are what cause the narrowing of the sound wave. These patterns are interference patterns, and they focus the beam. So the beam will start out large, come down, reach a focus, and then diverge. These are some static images of ultrasound intensities, and you can see the beam is actually narrowing down and then diverging. Okay. And that concludes our study on the shape of the sound beam.